Continuing our discussion of shell coding, we've looked at some 32-bit shell code for Linux, and now I want to show you the equivalent shell code with 64-bit Linux. It's pretty much the same with a couple of minor differences. System call numbers have changed between 64-bit and 32-bit. Here I want to put a 1 into AX, and remember that RAX is the really big AX as opposed to EAX, which is the extended AX. I still have access to things like AL, and here for the file handle, I'm going to XOR RDI with itself, and this time I incremented it to go from 0 to 1. Once again, I'm going to use my jump, call, pop, construct. I XOR RDX with itself, move 17, the length of my string, to DL, make my system call, etc. So this is essentially the same as our 32-bit code, but replacing E whatever with R whatever in most cases. So now, if I say I want to build this, NASM -ELF64, and I want to make simple no null ASM and output simple no null.o. That's done. I link it. I don't have to do anything special since I'm running 64-bit Linux. LD simple dash no null.o and output simple dash no null. By the way, it's a good idea to check and make sure that the programs still work. And they do. If I run my script on this new one, I can verify that, in fact, there are no null characters there. So we've learned how to do 32-bit and 64-bit Linux. How about Windows? So Windows is slightly different. We still have a global start, a text section, and here my code starts. Notice right away I have a jump short, I jump down here, I call, and I pop. So I am trying to get the address of this string here into EBX. Now, if I look at this string, it says command.exe/c calc.exe, and then this is a terminating null character that's been added to the end. So I load that address into EBX. I put 0 in EAX, and then Windows is different in that you don't use system calls, you just call functions. Another difference is the calling convention that is used is different. So here I push EAX on the stack, I push EBX on the stack, and then I move my address for my function. The function I'm trying to call is winexec. I move that into EBX. I call that function, and then I exit cleanly by zeroing out EAX again. I push it on the stack. I move the address of the exit process function onto my EBX register, and then I call that function. So in some ways, it's very simple, but it's definitely different from the case that we had with Linux. Now, if you're trying to write some shell code, there are a couple of questions that you might naturally want to ask yourself. And the first question would be, how in the world did I get these addresses for these functions? Now, one issue that you have with Windows, if you're writing shell code, is that the address of these functions can change from one version of Windows to another. And it's not just going from XP to Vista to 7, etc. It's different service packs. So you might have a different service pack level than somebody else, or you might have XP Pro, not XP Home, and suddenly this stuff doesn't work. So that is one thing that's a disadvantage when you're writing shell code for Windows. If you're writing shell code for Linux, you can't go around changing those system call numbers because you would have millions of people very unhappy with you. But Microsoft, on the other hand, they seem to feel free to change sometimes the interface to the calls and often the addresses to the calls. Before we get to how I found these addresses, how do you make shellcode out of this? again, it's fairly simple. This is 32-bit Windows, by the way. The process is similar for 64-bit Windows. If I go to my terminal and I say, all right, I want to build ASM-F ELF32, and I want to build Win32 shell.asm and output Win32 shell.o. I'm going to go ahead and link it. Now, this might seem a bit strange to link this with a Linux format. Don't worry about that because honestly, you're not trying to run this program. You're just trying to generate shellcode from this program. So here I'm going to link it, input Win32 shell.o, and output that to Win32 shell. By the way, the script that I'm using uses objdump. Objdump can be used to disassemble raw code. So if I run objdump on this code, -d, and I probably want to use -M Intel in order to get the Intel syntax that we've been using, I can run this on Win32 shell, and it will output my code and it will show me the disassembly. So here's the raw bytes that make up my program. Here's my jump, here's my pop, etc. None of these can be zero. So the little script that I showed you earlier allows you to take this and convert it to your string. So I run it, Win32 shell. Now I get this. And you can even verify in case you don't believe it. The last 3 bytes are 657865. And sure enough, here they are, 657865. So what I can do now is I can copy this and then paste it into my shellcode. So we're going to take another break. When we come back, we will show you how to actually execute this shellcode.